People of shockwaves. Albrecht Bethe. From stellar fusion to nuclear blast waves. In 1941, two physicists realized something profound. Behind a powerful shockwave, air doesn't instantly reach equilibrium. The molecule's vibrational energy lags behind their translational motion, creating a zone of non-equilibrium that fundamentally changes how the shock propagates. This insight would prove critical for understanding nuclear weapon detonations and atmospheric reentry. But it came from a man whose greatest achievement was explaining how stars shine by fusing hydrogen into helium in their cores. This is a story of Albrecht Bethe, the father of nuclear astrophysics, who became one of the Manhattan Project's key theorists and gave us the equations governing nuclear blast waves. Albrecht Bethe was born in 1906 in Strasbourg, Germany, now Strasbourg, France, the son of a university professor. He studied physics at the University of Frankfurt am Main, then moved to Munich. After taking his doctorate at the University of Munich under Professor Arthur Sommerfeld in 1928, Bethe began to teach theoretical physics at various German universities until 1933. As Hitler rose to power, Bethe fled Germany's growing Nazi regime in 1933. He went to England for the next 2 years, working in nuclear physics. He held a temporary position as lecturer at the University of Manchester from 1933 to 1934 and a fellowship at the University of Bristol in fall 1934. Together with German-British physicist Rudolf E. Piles, he developed a theoretical model of the deuteron shortly after his discovery in 1932. The deuteron, a nucleus containing one proton and one neutron, was the simplest composite nucleus. In February 1935, Bethe was appointed assistant professor at Cornell University in Ithaca, New York, where he would remain from 1935 to 1975. Bethe became renowned for his theory of how the sun and stars use nuclear reactions to supply the energy they radiate. This was astronomy's greatest mystery. What powered the stars? Partly in collaboration with U.S. physicist Charles L. Critchfield, Bethe proposed the proton-proton chain in 1938 and the carbon-nitrogen cycle in 1939, the latter dominating in hotter stars. The end result of the reactions is a fusion of hydrogen nuclei to form helium nuclei, converting mass into energy. 4 hydrogen nuclei fuse to create one helium nucleus, where the mass difference releases light and heat. This process was independently suggested at the same time by Carl Friedrich von Weizsäcker in Germany, the so-called B-Weizsäcker cycle. Bethe had solved stellar astrophysics' central problem. This work would earn him the 1967 Nobel Prize for Physics. At the beginning of World War II, Bethe, on his own, formed a theory of the penetration of armor by projectiles, published in 1945. But his most important contribution to shock-wave physics came in 1941. Together with Edward Teller, Bethe showed that behind strong shock waves of fluids such as air is in non-equilibrium because it takes a certain amount of time for the energy of the molecules corresponding to the vibrational degrees of freedom to arrive at equilibrium with the molecular energies corresponding to the translational and rotational degrees of freedom. Behind strong shocks, vibrational modes lag behind. The molecules are translating and rotating at high speed, but their internal vibrations haven't caught up yet. This creates a relaxation zone behind the shock front. For weak shocks, this is negligible. But for intense shocks from nuclear weapons or atmospheric reentry, this non-equilibrium effect fundamentally changes shock structure. Bethe began to work out a theory of shock wave propagation in dissociated gases, which became an important effect in the case of the detonation of nuclear weapons. During the war, Bethe worked for the Manhattan Project, leading the theoretical division of the Los Alamos Scientific Laboratory from 1942 to 1945. He was a head theorist calculating how nuclear weapons would work. In 1947, he edited the Los Alamos Report Blast Wave, Report LA 2000, one of his most cited works among shock physicists, which describes how a nuclear weapon blast wave develops over time and distance. Understanding blast wave propagation determined predicted casualties, optimal detonation altitude, and weapon design. For an arbitrary equation of state, He discussed theoretically the shock wave velocity in comparison to the sound velocity behind the shock front in 1942, fundamental relationship for any material under shock loading. Together with John G. Kirkwood, he worked out an analytical approach to shock wave propagation in water for a number of explosives, the so-called KIRKWOOD propagation theory, providing equations for underwater explosion effects. Later, he made contributions to the design of the heat shield for ballistic missiles when they re-enter the atmosphere. After World War II, Bethe worked extensively on the collision of charged particles with atoms and pursued his earlier research on stellar nuclear energy, for which he received the 1967 Nobel Prize for Physics for his contribution to the theory of nuclear reactions, especially his discoveries concerning the energy production in stars. He derived an equation of state of matter at supernuclear density, ρ 10 to the power 1 g OCM cubed, to determine the moment of inertia and mass of neutron stars in 1974. In 1978, he began investigating the behavior of matter in a collapsing giant star that, due to gravitation, gives rise to a supernova explosion. Throughout his life, Bethe remained vigorously opposed to U.S. H-bomb research, although after World War II he returned to Los Alamos as consultant. He was a member of the President's Science Advisory Committee from 1956 to 1959. At age 88, he called on all scientists to cease and desist from work creating, developing, improving, and manufacturing further nuclear weapons. In 1997, at age 91, he wrote to President Clinton that the time has come to stop sponsorship also of computational experiments, or even create thought designed to produce new categories of nuclear weapons. From 1944, he was a member of the U.S. Academy of Sciences and received its Draper Medal in 1948. He was president of the American Physical Society in 1954 and was awarded the U.S. Medal of Merit 1946, the Planck Medal 1955, and the Eddington Medal, 1963. He won the Enrico Fermi Prize, 1961. His main work was published in more than 250 papers. He wrote superb review articles and books on quantum mechanics, nuclear physics, and field theory. Hans Albrecht Bethe died on March 6, 2005 at age 98 at his home in Ithaca, New York, near Cornell University. From explaining how stars generate energy through fusion, to calculating how nuclear blast waves propagate, to advocating against nuclear weapons, Bethe's career spanned the full arc of nuclear physics. His theory of non-equilibrium behind shock waves, his blast wave report, and his KIRKWOOD theory remain fundamental. Hans Albrecht Bethe, the physicist who explained both how stars shine and how nuclear weapons destroy.